My today's topic is called, as you can see from the syllabus, it is known as Gram-Schmidt orthogonalization process. Okay, and first of all, I'm going to give you the definition of orthonormal basis. First of all, so what is the definition of orthonormal basis? Now you are familiar with each and every term. You are familiar with the term basis. You are familiar with the term orthonormal. So I think you will be able to understand by the definition itself, and it needs no explanation. What do we mean by orthonormal basis? So its definition is very clear from its context. Let capital V be an inner product space, and you know every definition which I am choosing from the book Friedberg. So if you are not able to write it, you can get it from the pages of the chapter of inner product space. Still, since I'm taking the class, it would be nice if I write it on the whiteboard. So it should always be in front of you. So let V be an inner product space. A subset of V is an orthonormal basis, is an orthonormal basis for V if it is an ordered basis that is orthonormal. Very simple definition. But this term is important. You have to choose an ordered basis which is orthonormal. And what is orthonormal? What are orthonormal vectors? Orthonormal vectors are those vectors which are, if we have a set, if we have a set of vectors, and if we choose any two pair of vectors, and they are orthogonal to each other, the set is called consisting of orthogonal vectors. And if these vectors are unit vectors, then those set of vectors is called orthonormal set of vectors. Now, if the set of vectors, that set of vectors becomes basis itself, okay, then, and V is the inner product space, means V is a vector space on which inner product is defined, and the V has a basis which is orthonormal, ordered basis which is orthonormal, then such a basis is called orthonormal basis. Such an ordered basis is called orthonormal basis. Okay, so very simple definition as it goes. Gram-Schmidt orthogonalization process actually tells us how to construct an orthonormal basis. Gram-Schmidt orthogonalization process gives us what? It gives us a construction. It is a construction by which we can produce an orthonormal basis. Okay, so I'm going to talk about this construction in today's class. I shall not delve into the details of this, but first of all, I'm going to give you the statement of Gram-Schmidt orthogonalization process itself. Okay, and with respect to the statement, I'm going to show you a problem. Okay, so first of all, statement of Gram-Schmidt orthogonalization process. Statement. And you very carefully listen. This is a very important topic. Okay, as it is, you see, it is there in the chapter 6, Gram-Schmidt orthogonalization process. In my research days, when I did research on quantum computing, we did Gram-Schmidt orthogonalization process. A number of times we used it. Okay, so that is the thing from my personal experience. I am saying is very useful and it's very important. And also I have come to know from one of the faculties of CSE department that in deep learning and neural network, Gram-Schmidt orthogonalization process plays a very vital role. Okay, so what you are learning now, please do not forget. Okay, you have a habit of forgetting things, so please do not forget. Let capital V be an inner product space, okay, and capital S consisting of a set of vectors W1, W2, Wn, and this set of vectors is a linearly independent subset of V. Be a linearly independent subset of V. Linearly independent subset of V. Define another set which we name as S prime, whose elements are V1, V2, Vn, where the first element V1 is same as the first element W1, but the other elements can be constructed in the similar manner. Vk can be constructed as Wk minus summation j goes from 1 to k minus 1, inner product of Wk comma Vj divided by norm Vj square Vj, and k lies between 2 and n, or we could have written as k is lying between 2 and n, or we could have written k equals to 2 to up to n. Okay, this is another representation of showing that k line runs from 2 to up to n. The construction of this set V1, V2 dot 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 Vn by the above rule is called Gram-Schmidt process. Gram-Schmidt process. Okay, so those who are copying, those who are taking pictures of this particular screen, I don't have to say anything to them. But those who are copying it, please quickly copy this particular section, because I'm going to go to the next page where I'll be using this formula for the construction of this particular set S prime. Now, if you ask me that what sort of questions, MCQ type of questions can be asked from this statement, I can give you two examples. So for example, I can ask, in Gram-Schmidt orthogonalization process, when we construct vectors from a set of vectors from another set, then the set from which the construction is made, that set, number one option, linearly independent, number two option, linearly dependent, number three can be any set, either linearly independent or linearly dependent, and number four, it has to be basis. Now the answer is linearly independent, because it has not been mentioned in the statement that this is a base, this should be a basis. Okay, now actually by this particular construction we try to find out a basis. We want to construct an orthonormal set of vectors. Orthonormal set of vectors actually plays a very vital role in studying things. Another question that can be asked, that in our Gram-Schmidt orthogonalization process, the set from which the vectors are constructed and the set containing the new vectors must have same number of elements, different number of elements. Number of elements in one set is less than the other. Number of element in one set is greater than the other. So in various way, this particular, or they can give you a formula and there suppose the square is missing, or in place of the square cube is there, or something else, Vj is missing, and they may ask you to find out the incorrect representation of the Gram-Schmidt. So if most of the times you are very much confused about what sort of questions can be asked, what sort of MCQ questions can be asked from this. So I always suggest students to go through the statements, because if you can remember the statements, you'll not be in a trouble. So let us solve a problem. Okay, let us solve a problem. Let us take this example, and I'm going to show you how to do this. In R4, we consider three vectors, W1, which is 1, 0, 1, 0, W2, which is 1, 1, 1, 1, and W3, 0, 1, 2, 1. Okay, we want to apply the Gram-Schmidt process, to the set S is equal to W1, W2, W3 to obtain S prime containing V1, V2, and V3. You don't have to check whether it is linearly independent, but it is obvious that this set will be linearly independent. So to begin with, you will always write, if the question is like this, you will write that it is obvious that the set capital S is linearly independent. And if you have time, you can show it. You can show it very easily that this set is linearly independent. You have to choose three scalars, multiply the scalars by the vectors, add them, equate it to 0, 0, 0, 0, because that is the zero vector of R4, and equate all the terms corresponding to with respect to its corresponding zero, and solve it. You will find that all the scalars are coming out to be zero. It's quite easy. So I'm putting a star over here because this checking is needed actually, but here I'm not going into that part because this has been done several times. Now the process, according to the Gram-Schmidt process, okay, the first vector V1 of S prime should be equal to W1, okay, and therefore V1 is same as W1, so 1, 0, 1, 0. Very good. Now this is my number 1. Now then V2 by the rule. Now you carefully observe what was the formula. Vk is Wk minus summation j goes from 1 to k minus 1, Wk Vj by norm Vj square Vj. That is the formula. So we shall write W2 minus, okay, put a bracket, summation j goes from 1 to 2 minus 1, W2, inner product of W2 and Vj by norm Vj square into Vj. Okay, now I am going to break the summation. So we are getting W2, and what you are getting over here, 2 minus 1 means 1. That means actually j goes from 1 to up to 1. Only one term will be considered. So W2 Vj by norm Vj square Vj. Okay, and this is nothing but, since j is running from 1 to up to 1, so that means actually we are considering only one term. So we can write it as inner product of W2 V1 by norm V1 square and V1. So once, what is happening, this vector once constructed, it helps you to get the new vector. So V1 constructed over here is being applied for the construction of V2. So I am going to calculate W2 V1 and norm V1 square below, first of all. Let me do it with different color. Now W2 V1, the inner product of W2 and V1. What is W2? W2 is this vector. So we are writing it as 1, 1, 1, 1. This is the vector of W2. And what is V1? V1 is this vector. So 1, 0, 1, 0. Okay. And in the last class, I told you in the set of Fn, how this inner product is defined, because in a particular vector space, how the inner product is defined, that is very important. And you can recall that the inner product was defined in the following manner: ai bi bar, I goes from 1 to n. If you can recall it, if you are studying at home, you can remember. So I can write it as 1 plus 1 into 1 bar plus 1 into 0 bar plus 1 into 1 bar plus 1 into 0 bar. Okay. And 1 bar is a real number 1 itself, so it is 1, and this is 0, and that is 1. So we are getting 2. Inner product of W2 and V1 is 2. And what is norm V1 square? What is norm V1 square? So norm V1 square is, norm V1 square means what? It means inner product of V1 and V1. Inner product of V1 and V1. Actually, there is always a square root sign, but here the square root will not be there because we have taken the square. What is V1? V1 is 1, 0, 1, 0 and 1, 0, 1, 0. So again, you shall use this rule, and you will get 1 into 1, that is 1, 1 into 1 bar, that is 1, 0 into 0 bar, that is 0, 1 into 1 bar, that is 1, 0 into 0 bar, that is 0. So 1 plus 1 gives you 2. And therefore, we can write here, so W2, put the value of W2. W2 is 1, 1, 1, 1 minus, what is W2 V1? W2 V1 is 2. What is norm V1 square? It is also 2. What is V1? V1 is 1, 0, 1, 0. Okay. And you can cancel these terms, and this becomes 0, 1 minus 1, that is 0, 1 minus 0, that is 1, 1 minus 1, that is 0, 1 minus 0, that is 1. So 0, 1, 0, 1 is the vector which is called V2. 0, 1, 0, 1 is the vector which is called V2. Now we are going to construct V3, and you can see that in construction of V3, both the V1 and V2 will be used. Okay. So if you have written, I can go to the next page. I'll again come back to this page, don't worry. So let's go to the next page for the construction of V3. Now V3, first of all, let us write the definition. So the formula. So it is W3 minus summation j goes from 1 to 3 minus 1, W3 Vj, inner product of these two, norm Vj square into Vj. Okay. So if you expand it, you will get W3 minus W3 V1 by norm V1 square V1 minus W3 V2 norm V2 square V2. 3 minus 1 is 2. So the summation will run from 1 to up to 2. Okay. Now, first of all, I'm going to construct this inner product W3 V1. What was the value of W3? What was the vector? It was 0, 1, 2, 1. And what was V1? V1 was 1, 0, 1, 0. 1, 0, 1, 0. Okay. And therefore, it becomes 0 into 1 bar plus 1 into 0 bar plus 2 into 1 bar plus 1 into 0 bar. And this gives us 0, 0, 2 and 0. Okay, so the answer is 2. And norm V1 square norm v1 square, it gives us inner product of v1 and v1, which is probably I have found it previously. Norm v1 square, norm v1 square has already been found, which is 2. So that is also 2, previously obtained. Okay, so we have got these two. We have got w3 v1 and norm v1 square. Again, w3 v2, w3 v2. Okay, so w3 v2 means put the vector w3, and what is v2? v2 was 0 1 0 1. So let us put it 0 1 0 1 and find this inner product. So this would be 0 0 bar plus 1 1 bar plus 2 0 bar plus 1 1 bar, and the result is 0 1 0 1. So it is 2. Okay, and w3 and norm v2 square, norm v2 square is inner product of v2 and v2. What is v2? v2 is 0 1 0 1 and 0 1 0 1. Okay, and this is what? 0 0 bar plus 1 1 bar plus 0 0 bar plus 1 1 bar, which is 2. So this term and that term has also been found. Then your v3 becomes, consider the vector w3. So w3 is 0 comma 1 comma 2 comma 1. What is inner product of w3 and v1? It is 2. What is norm v1 square? It is also 2. So we write 2 by 2. And what is v1? v1 is 1 0 1 0. So v1 is 1 0 1 0. And what is w3 v2? w3 v2 is 2. What is norm v2 square? Norm v2 square is 2. And v2 is how much? 0 1 0 1. So ultimately, if I calculate this, what do we get? Okay, and this would be just check the calculation, because sometimes I do silly mistakes. So therefore, I have subtracted. Is everything all right? Probably it would be much better if I do it in first. I subtract the second one from the first one, so it will be, so I shall be sure about the sign. So if I subtract this from that, we will get -1, 0 minus 1, that is -1, 1 minus 0, that is 1, 2 minus 1, that is 1, and 1 minus 0, that is 1. 0 minus 1 minus 1, 1 minus 0 1, 2 minus 1 1, 1 minus 0 1, and we are subtracting this from 0 1 0 1. Okay, now you subtract -1 0, that is -1, 1 minus 1, that is 0. Yeah, previous one was wrong because there was some sort of mistakes in the I mean the negative part. So -1 minus 0, that is -1, 1 minus 1, that is 0, 1 minus 0, that is 1, and 1 minus 1, that is 0. This is the correct one. I had some doubt in my mind because I here the minus sign, here the minus sign. So actually I subtracted. If I take the minus common, I mean, I had to add the things, but I subtracted it. So that was a mistake. So therefore, this is the vector, your v3. You have got all the vectors, all the three vectors. So the new set, the set of vectors is the set of vectors, set of new vectors are, what is v1? v1 is 1 0 1 0 1 0. So let us write it 1 0 1 0, and V2 is where V2 0 1 0 1. Okay, 0 1 0 1, and V3 is minus 1 0 1 0. Now this set of vectors is orthogonal vectors. This set is orthogonal set of vectors. Orthogonal set of vectors. This set is called orthogonal set of vectors. But if you want to get the orthonormal vectors, then what you need to do? You need to normalize the vectors. We need to normalize the vectors. And you know how to normalize a vector. In the previous class, I told you the vectors will be divided by its norm. The vectors will be divided by its norm. So here I am writing what is norm V1. What is norm V1? Norm V1 square was 2. So norm V1 is root 2. What is norm norm V2? Norm V2 was also, norm V2 square was also 2. So norm V2 is root 2. And norm V3, we have not found norm V3, so we can quickly do it. It would be norm V3 square would be V3 V3 inner product of these two, and therefore that would be minus 1 into minus 1 bar plus 0 into 0 bar plus 1 into 1 bar plus 0 into 0 bar. So that would be minus 1 bar means minus 1 into minus 1, that is plus 1. This is 0, this is 1, this is 0. So answer is 2. So that is also 2. So norm V3 is also root 2. And we only take the positive square root because norms gives you length and distance. So do not take the negative square root. If you are confused, I have come to know that some students are very confused about this and they are facing difficulties with linear algebra. So you have to be very careful. So once I do it, then we can write, I'm going to write in the next page. Then the set of orthonormal vectors which has been obtained from the Gram-Schmidt process, is, let us write is S ortho, and that would be 1 0 1 0 divided by root 2, 0 1 0 1 divided by root 2, and what was the last vector? Minus 1 0 1 0. So minus 1 0 1 0 divided by root 2, as the vector V when normalized takes the form V by norm V. Okay. Here in this particular mathematics, we are considering the vectors as, we're writing the vectors simply as V1, V, W, V1, W1. In this way, we are writing the entire vector space. We are mentioning the vectors as this. When you study physics, we just put a bar on that, arrowhead on that, and we call that these are the vectors. In case of physics, this we write in case of mathematics. In case of physics, we do so. And if we talk about quantum physics, then these vectors are denoted by this Dirac notation. So here the dress change, but the meaning remains the same. So all these things will have the similar properties. In physics vectors, the classical physics vectors, the Gram-Schmidt process, entire thing can be applicable, will be applicable. In maths, we are doing maths because maths generalize things. And in quantum physics also, the Gram-Schmidt process is very, useful. So in quantum physics, if when people write Gram-Schmidt process, in quantum physics, when people want to write Gram-Schmidt process, they write it in this following manner. They write V1 is equal to W1 and WK is equal to, no, not WK, and VK, this is equal to WK minus summation J goes from 1 to K minus 1, and the inner product is represented in the following manner, WK and VJ. This is the representation of the inner product. The same thing which I have written like this, WK comma VJ, they write it in the following manner. Okay, and norm is written the same way as it is, but only the vector notation is introduced. So we write it in this manner and multiplied as the vector Vj. This is the representation of the Gram-Schmidt formula in quantum physics. So if you see it, and suddenly you have a habit of to differentiate things from similar kind of things from one another. You learn something here, and then if it is applicable there, and you see that is written in another form, you say, oh, it is something different. Sir has never told us the Gram-Schmidt process can be written like this also. So that's why I'm telling. Suppose maybe in deep learning and in the neural network, it is written in some other way. Okay, so I don't know. Probably they use the same mathematical notations, but therefore I'm telling you that yeah, this is the notation. Keep it. The basic structure remains the same. Only the notations have, the vector notations have changed. Okay, so you remember this. You always have a habit of mixing things up, and then you mix things, but you cannot recognize your own mixing. So therefore, be careful when you learn something. So that's how then by the Gram-Schmidt process, this vector orthogonal vectors are considered, and from orthogonal vectors, by normalization process, we can construct the orthonormal set of vectors. Another definition is also very important. It is not the definition of Gram-Schmidt process, it's definition of orthogonal complement, and that I must put over here. So let us write it. This is also very important. You have to remember this. Let capital S be a non-empty, let S be a non-empty subset, S be a non-empty subset of an inner product space V, of an inner product space V. We define S bar, S perpendicular, to be the set of all vectors in V that are orthogonal to every vector in S. Okay, every vector in S. And then S perpendicular is the orthogonal complement of S. S perpendicular is the orthogonal complement of S. I hope you have understood And this particular discussion actually completes module 5 of our syllabus. Okay, so I am not taking any further session in today's class. This is the last session. Those who have not mentioned their roll numbers in the chat box, they can do so now. I'm going to end the session for today, and many more things were to be discussed from. I was supposed to discuss many things from this particular chapter of inner product space, but because of this sudden, I mean, notice from the MACOUT end that the examination will be, as the examination is knocking at the door, so I'm not going to feed you with new topics, okay, and extra topics, because the extra topics, since they are not mentioned in the syllabus, so I'm not going to. But I'll suggest that you can read the definitions like self-adjoint operator and etc. Many things are there, adjoint operator, of adjoint of linear operator, etc. You can study it from the book itself if you like. So and see the problem which I've shown you, over here. This problem is where the inner product which was defined on Fn has been used. But there are some other examples of the vector spaces where inner products are defined in a different way. Okay, so with respect to the vector space and the inner product defined on it, with respect to the vector space and the inner product defined on it, we shall have to calculate accordingly. We don't apply this result everywhere. This inner product is applicable to Fn only. Remember this. So you have to study now and go through the statements and the chapters, everything properly. So this is for this much for today. See you in the next class. If I have with some topics, if I have something to discuss with you, then we shall discuss once again. So today I'm going to conclude the session at this point. Okay, you study and best of luck.